2 diamonds, a microscopic sample, and enough force to approach the crushing conditions at the center of the Earth. We cannot physically drill down to the Earth's core to study its environment. The intense heat and pressure make direct observation impossible. Historically, recreating extreme high pressure in a laboratory required massive multi-ton industrial machines. They were heavy, iron, and entirely opaque. The modern solution is the diamond Anvil cell. It is a handheld piston cylinder device designed to hold 2 opposed diamonds perfectly aligned. A thin metal gasket is placed between the 2 diamonds. It contains a microscopic hole that acts as a tiny containment wall, preventing the sample from squirting out as the pressure builds. To study the largest physical body we know, the deep interior of our own planet, researchers had to build one of the smallest pressure chambers ever engineered. Diamond presents a unique paradox for this kind of work. Its extreme compressive strength makes it the ultimate physical barrier, while its optical transparency makes it the ultimate window. The pressure is applied at the culet, a microscopic, perfectly flat tip ground onto the diamond. This animated equation visualizes a basic rule of physics. Pressure equals force divided by area. A moderate physical force applied to the wide, flat back of the diamond is multiplied exponentially as it funnels down into the tiny surface area of the culet. The cell achieves extreme pressure through exact geometric concentration, rather than brute mechanical force. Once the chamber is sealed in crushing the sample, researchers face an immediate obstacle: measuring the internal pressure without destroying the gauge. To solve this problem, scientists place a microscopic fragment of ruby directly into the sample chamber before tightening the cell. This graph displays what happens when a laser hits the ruby. Chromium impurities fluoresce, emitting 2 specific red wavelengths. As the diamonds compress the ruby's lattice, those emission wavelengths shift toward the infrared spectrum in direct proportion to pressure. That glowing stone acts as an optical broadcaster, reporting violent internal conditions to the outside world. While the cell itself fits in the palm of a hand, it is regularly transported to massive kilometer-wide synchrotron facilities. These facilities generate intense, hard X-rays that pass directly through the diamond window, revealing the exact crystal structure of the compressed matter. Simultaneously, lasers are fired through that same transparent barrier, heating the sample to thousands of degrees to recreate the boiling state of the Earth's core. Because the diamond is electromagnetically transparent, researchers utilize a vast array of spectroscopic and observational techniques. The instrument serves a dual purpose. It generates the necessary pressure while providing the clear window required to watch matter transform in real time. The standard flat culet has an absolute physical limit. At extreme, ultra-high pressures, the diamonds begin to bow elastically, and eventually they shatter. To push past this barrier, engineers developed toroidal diamond anvils. This schematic compares the standard flat tip to the toroidal design, featuring a central column surrounded by a microscopic moat. Under extreme load, the extruding metal gasket flows outward, becoming safely trapped within that trench, preventing the structure from failing. This precise geometry allows the cell to surpass 500 gigapascals, comfortably clearing the 360 gigapascal pressure found at the Earth's core. By altering the physical shape of the diamond itself, physicists bypass traditional high-pressure containment limits. Every major breakthrough in high-pressure physics begins with the precise mechanical alignment of these tiny surfaces. The instrument has allowed researchers to predict the iron cores of distant exoplanets and force mundane materials into entirely undiscovered quantum states. To understand a violent, inaccessible world thousands of kilometers beneath our feet, we rely on an observation chamber smaller than a single grain of sand. Thanks for watching Rarecraft Archives. Subscribe for more explorations into the mechanisms of scientific discovery.